Buffon's needle project. To start, we are going to discuss pi. Pi is the ratio between the circumference of a circle and its diameter, and is a constant with every single circle. Pi is commonly used in math class for geometry, polar coordinates, trigonometry, and repeating cycles. But outside of the classroom, pi is found in art, architecture, engineering, manufacturing, space, and so much more, even nature. Today we are going to calculate pi using probability. First, we are going to consider a circle inside of a square with a length of 1. This would mean the radius is 1/2, and we are going to calculate if a dart was thrown randomly, what would be the percentage of the dart landing inside the circle. To do this, we are going to take the area of the circle and divide it by the area of the square, and then times it by 100 if you want the probability in a percentile. Alright, so our next step is to consider a square inside of a circle with a radius of 1, and if a dart is thrown randomly, what is the probability that the dart lands inside of the square? So first we are going to create a hypotenuse with the radius of the 1 on the square, and we're going to break it down into triangles, and then we're going to evaluate the sine of 45 with the hypotenuse of 1. That is one of our unit circle answers, so we're going to get the square root of 2 divided by 2, and then we're going to take the area of the square and divide it by the area of the circle to find our probability. Just some quick math to show you how I got the evaluation. And then the area of the circle is just pi because the formula for the area of the circle is radius squared times pi, and that is just pi because the radius is 1. Buffon used geometry to create ratios of chance, just like we just did. He was interested in this because he was a gambler, and he created gambling games based off of geometry and those ratios of chance. A today example of a game similar to Buffon's is skee ball. You land somewhere different every single time, and the probability that you land somewhere good isn't very high, but it's all based on geometry. One example of Buffon's games is the open tile game. Here I sketched the plot. Please pretend the squares are equal in size, and same with the coin. Buffon was interested in calculating the probability the coin would land in a square or multiple. To calculate this, he would need the area of the coin and the area of the shape, which in this case are squares, along with some idea of the center of the circles compared to the width and length of the shape. For example, if the length was less than the radius of the circle, this comparison is important for later. Another game Buffon thought of was a checkerboard and dropping a sewing needle onto the checkerboard and just seeing how many checkers pieces the sewing needle crosses. What would depend on this is the length of the sewing needle and its angle, and then the length of the little checker squares. And yeah, there's a few examples of potential ways it could land. So after the checker problem, Buffon thought of if there was just some floorboards with the one-directional cross sections. And if you see here, there's the needle, and the radius is equal to the distance between the made joints. So if the center of the needle is below the line AB, then it is impossible for the needle to cross AB. And then that would also depend on the angle of the needle when it's dropped. But if that center point is below, then it is impossible for it to cross. And that is something that Buffon really thought about. Here are some examples. Buffon only has to calculate the probability of the one side because everything is symmetrical from the needle to the floorboards. Buffon's quarter circle for the needle is important because a needle is symmetrical over the radius, and although it could point 360 degrees, if you could have either side of the needle B, E, or F, then you can deduct the probability to just C. Well, the the radius to being just C and then its position. The total positions the needles can land can be simplified into just this 90-degree angle. This part I had to annotate a little bit differently than Buffon, because if I did the same way he did, it would go over my head. But basically I had to take the area of the square AB and then AC, and then multiply it by B sine theta to find all the possible positions the needle could land if it landed in between the lines A, B, and CD. And then B is always greater than or equal to the radius of EF. B sine theta is basically just the arc of C, but I had to put it this way so my brain would understand it. So although my notation is a little bit different than Buffon's, it basically stood for the same thing. All right, I put all our notes up there. B is going to be less than or equal to the radius of EF, and it's going to be equal to it when the sign is equal to 1. We're going to write that down real quick. B is basically that Y horizontal of when the needle is dropped. It can be equal to 0 too. And then A is going to be equal to our radius of EF, and this is for just this case because, yeah, our length of the joints is equal to that radius. Okay, so now we're going to get into a little bit more of that advanced mathematics part. It is very important to remember that B is equal to C, and that is a half circle, but we are going to put it in terms of B and then sine of theta. And then A is a constant value that is the length of the joints, and that is also important because that gives you the area of the underneath it. It's going to be just like our first two problems where we're taking that area of the circle inside of the square, and yeah, that's how we're going to calculate our probability. We're going to take the interval. So in Buffon's experiment, the probability of crossing the needle was 2 over pi, and this is because B is actually equal to A, so then those cancel out. In 1901, this Italian guy named Mario Luzzatini did Buffon's experiment, but his needle was 5 over 6, the length of the floor tiles, so B was equal to 5 over 6A. And doing this, he got a different probability. At his time, pi was known to be 355 divided by 113, which the values are down below, but you can't really get an exact value of pi. It's an irrational number, but I mean, it just shows how close that fraction is to pi. So now we are going to evaluate it with Mario's experiment. So C is going to be equal to the number of needles that cross, and then N is going to be equal to the total of number of needles thrown or dropped. And what we're going to do is we're going to plug in our new A value, our new B value, which is 5 over 6 of the A, and we're going to get our value for pi because he has a physical number of how many he crossed and then how many that he thrown, and we're going to evaluate pi using probability. So Mario did the experiment 3,408 times, and 1,808 landed. So we're going to plug in those numbers for our formula here. And then we're going to simplify it so that way we can understand where his numbers came from and exactly what he wanted out of it. Simplifying these fractions are important because we get these important values of 213 and 113. The 213 times the 2 times 5 divided by 6 is equal to 355, which is significant because that is the fraction that Mario was aiming for, divided by the 113, which is the bottom, which was the known value for pi back in Mario's day. So doing this experiment, he was able to get the closest number to pi he could imagine. All right, so now I'm going to calculate pi using Minecraft, and we're going to start off by
our B value, which is our needle, which is going to be an arrow, and then our space between the lines is actually going to be 2 blocks. And an arrow, I had to look online, and online they were saying it was half a block, and I measured it myself and it was definitely more than half a block. But then another source was like it's a full block, and it's definitely smaller than that. So I went with 3/4. So my arrow measurement might not be exactly right. And now here I'm going to figure out our probability of getting the arrow to cross the line, and then we're going to figure out pi using that. So here's our formula, 2b divided by a over pi. That crosses out because a is equal to 2, so then we're going to get 3/4 over pi, which is going to be equal to our probability, and now we're going to have that be our number crossed, our crossed divided by our number of arrows in total, and then with some quick algebra, we're going to get that. We're going to find what pi is equal to. Give me just a second. So pi is going to be 3 and 4c. And then here's just a quick video of the setup for this experiment. Since I am in Bedrock and not Java, skeletons will hit you correctly like 99% of the time. So I had to be moving in order for these arrows not to be hitting me. So I went in a minecart and I had them go around me, so that way they would be shooting me at random different angles. And obviously my moving also helped to create that random angle speed. But yeah, I had to be moving or else these arrows would have hit me correctly every single time. And actually had the issue of it hitting my minecart quite a bit, like it just did there. And then I'd go into creative and then take a screenshot of the data. So I took multiple screenshots and each one gave me pretty different answers, but hopefully the averages are pretty close to pi.
So I got my n value to be about 151 and my c value to be about 37. So we're going to plug in my numbers here. If I did this into infinity, I could probably, in theory, get the correct value of pi, but since I didn't do all that many trial runs, it took a long time to do them, I'm happy with my number of 3.06. And I find it personally pretty interesting. We can get pi from even something as simple as Minecraft using geometry and all that. I did get the inspiration for the buffon needle part using Minecraft from a YouTuber. However, we used different mobs and different needle sizes for our calculations. So although I got the inspiration from him, it was definitely a different project.